Hi students, this is a lecture series on digital system testing and testable design, module 2, part 1. I'm Seema Safar, assistant professor, Rajagiri School of Engineering and Technology. Module 2 discusses on the following topics as you can see in the screen. It discusses on fault modeling, logic fault models, fault detection and redundancy, fault equivalence and fault location, fault dominance, single stuck faults, and finally multiple stuck faults. In this lecture session, we'll be discussing on the first part of fault modeling, which includes the topics till fault dominance. Let's discuss on the first topic on this module 2. Fault modeling, logical faults. Logical faults represent the effect of physical faults on the behavior of model system. In this module, we'll be considering only the fault that will be affecting the logic function. A logic fault model, it can be of two types. It can be either explicit or implicit. An explicit fault model defines a fault universe in which every fault is individually identified and hence the faults to be analyzed and it can be explicitly enumerated. Whereas an implicit fault model, they'll be defining a fault universe by identifying the fault which is of interest or on demand, typically by defining their characterizing properties. Now let's discuss about structural fault models in logical faults. Structural fault models assume that the components are fault-free and only their interconnections are affected. Now, how can the interconnections be affected? In a logical circuit, the interconnections are affected either by shorts or by open. Now, what do you mean by a short in digital point of view? A short is formed by connecting the points which is not intended to be connected, whereas an open results from breaking of a connection. Let me tell you a typical example of a short. A short between ground or power and a signal line can make the signal remain at a fixed voltage level. Alright, so since a short is between two signal lines, it creates a new logic function. Now the logic fault representing such a short is referred to as a bridging fault. So a bridging fault happens when the interconnections have a short. Now talking about open, the effect of an open on a unidirectional signal line with only one fan out is said to make the input that has become unconnected due to the open assume a constant logic value, and hence they'll be appearing as a stuck fault. So usually an open results in a stuck fault and a short result in a bridging fault. This figure depicts stuck faults that we have discussed in our previous slide caused by opens. The first picture shows a single stuck fault and the second picture depicts multiple stuck fault. This figure is taken from the reference text and the text is listed in the reference slide at the end. Now we'll discuss on a new topic, fault detection and redundancy. This topic is planned in 3 sections. First, we'll be discussing on fault detection in combinational circuits, followed by detectability of fault, and finally redundancy. Let's see each topic in detail. Now let's discuss about fault detection in combinational circuits. Before moving on to any of the technical terms like fault detection and redundancy, let's begin how we can formally define a circuit. As we know, any circuit is uniquely represented using a function which is called as logic function. This we have already discussed in our first module. Let z of x be the logic function of a circuit n, where x inside z represent an arbitrary input vector. Then z of x will be denoting the mapping realized by n. It means Z of X is going to denote the output of the circuit. So normally a faulty circuit means what? Some kind of error or a fault has occurred in that particular circuit. Now the presence of a fault F transforms N, which is the circuit N, into a new circuit NF, and that is going to have a new function ZF of X. Now see, Z or Z of X is transformed into ZF of X. So that will be denoting, F will be denoting a fault that has occurred to deviate from the original value, which was supposed to be given by the particular circuit. Hope this is clear. Now let's see how a test can be denoted. Usually a test is denoted by T, a specific input vector, test vector, and the response is denoted by Z of T, and N is the circuit. Now then we'll call a sequence of test vectors by test capital T, that is equal to a set of test vectors T1 till Tn. So a circuit is tested by applying a test T and by comparing the output response with the expected output response of N. Now let's discuss about how a test vector can be used to detect a fault. A test vector T detects a fault F if and only if Z of T is not equal to ZF of T. Now recollect, what is Z of T? Z of T is the output of a circuit without fault, and ZF of T is the output of a circuit with fault, where F will be denoting fault. If in the presence of fault the output is going to deviate from the correct response, then we say that that particular test T has detected a fault F. Alright. Now another terminology that is to be kept in mind is fault sensitization. A line, when is a fault said to be sensitized? A line in a circuit whose value in test T changes in the presence of fault F. In that case we'll say that it is sensitized, or that line is sensitized to the fault F by the test T. Mostly we'll say that test T is going to activate a fault F. Alright. Usually a test T is going to activate a fault F. Now another terminology is sensitized path. A path which is composed of sensitized lines is called as the sensitized path. Now usually we say that the test T, we have a test T, see, our test T propagates a fault F along the sensitized path. So usually we say that test T is going to activate F. If that test T is going to activate F, then it means that test T is going to detect an F if this condition is met. Hope this is clear. Now let's discuss about fault detection and sensitization with the help of a diagram. As you can see in the figure, this figure denotes a circuit, and A is a line which is sensitized with a fault A by 0. Now we are inputting a test vector 1 1 0 1, and that is simulated into this particular circuit. Now our aim is to detect a fault, right? So we have studied that a test vector will be activating a fault and it will be propagating the fault, and that path is called as sensitized path, right? So we are inputting a test vector 1 1 0 1, and as you can see here, this line is connected to a line A, supposing it be A, and assume that this is a faulty line with a fault A by 0. Alright. Now even though one reaches here, since it is a faulty line with a fault A by 0, it gets converted into 0. And this particular fault is propagated to the next level. Though the rest of the things work correctly and 1 was meant to come, if 1 was the correct response, since it's an error propagation or a fault propagation being happening, it gets converted to 0. Now on moving, now the error gets propagated in this output and finally to the primary output. Now the bold line or this path is called as sensitized path. So a test vector will be activating a fault. Hope this is clear. Now let's discuss about redundancy in circuits. A combinational circuit that contains an undetectable fault is said to be redundant. So the point that is to be noticed, undetectable stuck fault is said to be redundant. So it's a stuck fault which is stuck at a particular logic value. Either it can be stuck at a logic 0 or it can be stuck at a logic 1. But note that it is an undetectable stuck fault. In that case, we'll say that that particular combinational circuit is said to be redundant. How can we solve this issue? Now consider a situation where we have SA1 fault which is stuck at one logic value 1 fault on an input of an AND gate, and that is undetectable. Now why is it undetectable? Because since the gate does not change in the presence of fault, how can we solve this issue? We can permanently place a 1 value on the input. So we can say that an n input AND with a constant 1 value on one input is logically equivalent to n minus 1 AND, which is obtained by removing the gate input with constant signal. Similarly, if an AND input SA0 which is stuck at 0 is undetectable, then how can we solve that? The AND gate can be removed and we can replace it by a 0 signal. Now these are some of the simplification rules that we have to follow if we get to have an undetectable stuck fault. If it is an AND input SA1, remove the input. If it is an AND input SA0, remove gate and replace all zeros by 1. Please have a look at it. So we can say that a combinational circuit in which all stuck faults are detectable is said to be irredundant. So redundancy can be simplified by making use of these rules, simplification rules. Hope this is clear. Fault equivalence and fault location. Two faults F and G are said to be functional equivalent if a particular condition is satisfied. That is, ZF of x is equal to ZG of x. Now a test T is said to distinguish between two faults F and G if ZF of t equal to ZG of t. Now such faults are distinguishable. There is no test that can distinguish between two functionally equivalent faults. Now let's discuss about fault location. In addition to fault detection, the goal of testing is fault location as well. We need to apply a test that not only detects the detectable fault but also distinguishes among them as much as possible. A complete location test distinguishes between every pair of distinguishable faults in a circuit. Now, if F and G are two distinguishable faults, they may become functionally equivalent in the presence of an undetectable fault. Fault dominance is the final topic of this session. If the objective of a testing is limited to fault detection only, then equivalence, another fault relation, can be used to reduce the number of faults that must be considered. Now, the formal definition of a fault dominance is, we have a set of all test vectors Tg that will be detecting a fault G. Now, a fault F dominates G if and only if F and G are functionally equivalent under T of G. Now, what does that mean? If F dominates G, then any test that detects G will also detect F. Therefore, for fault detection, it is unnecessary to consider the dominating fault F, since by deriving a test for G, we automatically obtain a test that detects F as well, right? So that is the formal definition of fault dominance. So these are some of the terminologies that you should be knowing when you're studying a fault modeling thing. So by this we come to the end of this lecture session. The reference textbook for this session is listed here. Thank you.